As usual, you get first.
Well, I think the question we've discussed a lot is we have these very simple computations of decoherence time, decay, using either the upper and lowers or the negative probabilities, much simpler than the Hilbert space computation. And the question is, can that really be defended on its own physically? I think is really an interesting question. Because the computations are so much simpler. But can they be defended as physically correct, you think? What do you think?
No idea. I hope so. But yeah, that's a good question.
Can one be derived from the other?
Well, they're on sort of independent tracks, in a way. I mean, they clearly have, they're going to be close. In fact, we show in one paper we wrote that we can get, they do essentially the same thing. But it isn't it's the fundamental derivation of that decoherence time. I think it's the most interesting physical question here. It's so simple and elementary in the case of the upper probabilities or the negative probabilities. And that same computation, numerically, is tortuous carried through the Hilbert space formulas.
But well motivated by quantum mechanics.
You know, that's perhaps also a question. That could be discussed. So we'll leave it as a question.
So one of the advertisements for decoherence, it was going to deal with this mysterious collapse of the wave function, okay, by having a continuous transformation going forward. You know, these upper and lower, the calculations easier is Pat's basic claim here, but you're going to get the same answer as the Hilbert thing when you carry out a decoherence calculation. It's just an easier calculation, but basically the mysterious collapse has still gone away via decoherence.
No, the collapse is still there. Decoherence doesn't solve the measurement problem. What you show is that you end up with a mixture or so, but which of the options is realized is then still not explained. Yeah? And our work on uppers and lowers doesn't contribute at all to this. Yeah? So we are operating in the framework of standard quantum mechanics. We are not changing anything. We are just, well, it's about the foundations of the theory. Yeah? And that was the point I wanted to make, that we can mess around with the algebra or we can mess around with the probability. Yeah? Both lead to the same predictions, which are confirmed and which are, that's quantum mechanics. But we think it's more interesting to keep the algebra fixed and to play with the probabilities. But that doesn't solve any problems that one would not be able to solve with standard quantum mechanics. And the measurement problem is a problem. That's all. Good us.
One more question?
I guess I'm a little confused about what it means to keep the algebra fixed. I mean, one is you start with the Hilbert space. This is the classical thing. I mean, you have the probabilities defined there. You have Gleason's theorem as some kind of representation theorem. That all fits with this quantum logic in this very abstract way. So as long as you've got the Hilbert space, what that guy said was right. Namely, you can represent it that way. In many ways, a natural way. Yeah. So now what we're going to do is we're going to have axioms for probability, just that are abstract, no Hilbert space anyway. Right? But I don't know if this was the question. I mean, is there going to be a representation theorem for that probability theory that says there's going to be some kind of Hilbert space?
Or vice versa.
Huh?
Or vice versa.
Or vice versa. Right? I mean, so that if the Hilbert space is still there, I mean, what is it your gut feeling about this? Do you think that you're going to have a more general structure than Hilbert space, and that's the algebra now? Or are you going to have a representation theorem that's just going to get you back to Hilbert space? Or what?
I think it's the latter.
The latter. But then there will be some answer, maybe it will be complicated, to your question about how do we get this convergence. I mean, it will be some kind of convergence from the Hilbert space where, you know, some planes get really close together so that it's almost classical, just like you almost have joint distributions.
I mean, what I was focusing on was this claim of quantum logicians to use a non-Boolean algebra.
Right. But there is a non-Boolean algebra in the Hilbert space. The whole algebra is not Boolean. Where did it go?
Yeah, but okay.
I think the interesting question, I mean, the apparatus is very much simpler. You certainly cannot derive the Hilbert space within that. You have to have something much extra go. And I'm more skeptical than Stephan is about the Hilbert space. I mean, I think it's not very natural in many ways for many
That's what I thought.
problems. And so that doesn't mean, though, I'm not suggesting I have a good quick answer, but how are you going to replace it? I mean, in a way, you see, these computations, we accept them because they can agree with the Hilbert space, and we need to have a deeper understanding than we do now.
Well, there are contexts where you can really isolate a system from its environment and make decoherence a very, very, for example, very slow and very, very controlled process, where you can study it in detail. One photon comes in at a time, and slowly, 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 the system is made decoherent. Isn't that a context where the Hilbert space representation of everything is completely under control and where you can really calculate and do things?
That's what we are using here for the atoms, and a cavity or so.
And we
can control
know that it's correct, experimentally correct. So it looks to me like there's only room for reinterpretation, but I'm going to button my lip right here.
Yeah.
Okay, if there are no more questions, I assume there are no more. We'll move to the next.